Hi, welcome. I'd like to thank you for tuning into my talk today. My name is Andrew Berns. I'm an assistant professor at the University of Northern Iowa, and I'm here today to talk about my paper for SSS 2021 titled Network Scaffolding for Efficient Stabilization of the Chord Overlay Network. An early version of this work did appear as a brief announcement in SPA 2021. In this version, we will hope to elaborate a little further on our results, as well as have some improved bounds on performance. So let's dive right in. What kind of problem are we looking at? So we're looking at overlay networks where connections happen over logical links, where each of these logical links can be made up of 0 or more actual physical links. For instance, let's imagine that we have a bunch of computers distributed around the world. They're all connected to the internet, which I've represented naturally as a cloud. And the topology, the physical topology for many of these devices is actually fixed. They're plugged into a wall or they're wirelessly connected to a router in my home, and then they go to, say, my ISP. And so I can't actually through the physical links, create direct connections with any of these other devices inside my network. However, if I'm using logical links, I can say, okay, over top of these physical links, I want you to create a logical link that makes it, say, look like I have a ring topology. So even though this mobile device doesn't know or isn't physically connected directly to this PC, if we say know the IP address, or we can make that logical link to connect the two devices. The benefit of using these overlay networks in scenarios like this is that it's more efficient for finding, storing data, searching for data, doing efficient routing, things like that. So I can go from the completely unorganized, unstructured internet, impose logical links over top of that to actually make networks, groups of related entities that I can share data with and communicate with. Now, of course, as these devices are distributed, failures are going to happen. Failures could happen for a number of reasons. We might have, for instance, a link fail. So in this case, maybe the two ISPs, something in the internet has broken, a fiber optic cable was severed, something, and now I can no longer communicate with these two computers can no longer communicate because the physical link that realized their logical link has been severed. Also, it's not uncommon to have devices leave the network completely. So for instance, this mobile device maybe ran out of battery or was dropped or went in an elevator, whatever, it lost connection. When that happens, my network gets disconnected or at least separated. I may not be able to reach everybody else or find the resources I need because the network is no longer the topology that I thought. So what we'd like to have happen is when those kinds of faults are found, to have the algorithm or our systems automatically detect that they were in a bad configuration, and then take corrective action by, say, finding a new way to a new logical link to connect these, or making a new link that bypasses this missing mobile node, something like that. And then our routing and our data storage and searching, those kinds of things can still be done efficiently on the old operation. So that's kind of the goal that we're looking at with self-stabilizing overlay networks. We're certainly not the first to look at this idea. Just a few examples of some other work. Some of the earlier work from 2007 with the linear network, where after any transient fault, the network would automatically restore to a sorted list topology. The skip plus graph from 2009. Is another, it's a variant of the skip graph data structure with some additional edges so that faults can be detected. That actually could be built in polylogarithmic amount of time and from any initial configuration or after any transient fault. Chord looked at can we build a variant of the Chord network from 2011. And then multi-skip graph kind of expanded and said, not only can we build a correct network from or after any transient fault, but can we also ensure other properties as well? Like, is it if we if we can search for an item at one point in time, is it true that in all future points of our algorithm we'll still be able to find that item or maintain the property of monotonic searchability. So certainly we're not the first to look at that, but we are the first to have a polylogarithmic convergence time and space for the chord overlay network, and we'll talk about how we're going to get there. First of all, a little bit more about our model. We're going to be dealing with a standard message passing model. We have n processes, lowercase n processes, which will represent as nodes in the graph. Each process is assigned an immutable identifier in the range of 0 to capital N, where capital N then is the upper bound on the number of nodes in the system. Nodes can communicate over reliable message passing channels, synchronous, meaning in every round a node can receive messages that were sent to it, do some local processing, and then send messages to its neighbors. We will assume, and those communication channels are represented by edges in our graph. We will assume that the communication channels are reliable and bounded capacity, meaning if a message is received by a node, it must have been sent by another node from our algorithm in the previous round. So a message is delivered if and only if the message was sent by our algorithm. So we'll assume reliable communications on those. The big part with the overlay network model is that edges are now part of a node's mutable state, meaning we can change the topology through program actions. Let's imagine that node 14 here wishes to connect nodes 3 and 54. Node 14 could introduce 3 and 54 and add an edge to the network, because these edges are not physical entities, they're logical entities that's part of my state. Similarly, we could delete edges if 5 and 93 decide that they don't need to be connected anymore. They can remove that part of their state. So again, because edges are mutable, they can be added and deleted. Now, we'll call our networks self-stabilizing if they guarantee that a legal configuration can be built after any transient fault, or sometimes modeled as starting from any weakly connected configuration. So let's say that I start in this configuration down here on the bottom, but my target configuration is this. If the network is self-stabilizing, it will add and delete edges until eventually this correct configuration is reached. Ideally, or how do we measure the performance of a self-stabilizing algorithm? We'll look at two things. For the time, we'll look at the convergence time, which is just the maximum number of synchronous rounds that are going to be required to start from any topology and build the correct configuration. And we'll also look at the degree expansion, which is going to be the ratio of the maximum node degree during convergence over the maximum node degree from the initial or final configuration. The idea there is trying to capture how much extra our degree grows outside of the influence of our, or outside of factors outside of our control. So if we start with a high degree or we have to finish with a high degree, we can't expect our algorithm to maintain low degrees. And that's what the degree expansion is about. How many extra edges are you adding that are part of your control, ignoring those other factors? We're going to take a look at another type of network, which we'll call Avatar. This is actually something that's based off of a work we did in 2015, where we had Avatar CBT. Avatar was a way of defining a network, a dilation 1 embedding from a set of real nodes onto a set of virtual nodes. In this example, we were using Avatar CBT for complete binary tree. And the goal was to embed this binary tree. So in this example, capital N15, embed this 15 virtual node complete binary tree onto these, in this case, n equals 4 real nodes. To do that, what we did is we basically created like a linear network, a sorted list. Nodes were then capable of determining their predecessor and their successors. And using that information could determine what identifiers, what virtual nodes they were responsible for hosting. and then they could go ahead and add and delete edges in the real network so that it was a dilation 1 embedding. That is, if two virtual nodes are neighbors in our virtual network, their hosts are neighbors in the real network. And so here it's color coded. We'll see the blue node over here has an ID of 10. And so it's going to keep track of virtual nodes 10 all the way up to 15. So 10, 11, 12, 13, and 14 stored in there. The benefit of using the embeddings as defined by initially the predecessor relationship on the linear graph is that it's actually locally checkable. So for any topology that I define of a fixed set, capital N number of nodes, I can take an arbitrary set of nodes in the real graph, connect them together, and then using their state and the state of their neighbors, they can determine what nodes should I be hosting to realize a dilation 1 embedding, and what neighbors should I have to realize that dilation 1 embedding. And so it gives us local checkability. It turns out we can actually build that complete binary tree relatively quickly. So we found that we can we can stabilize in order log squared n in expectation. There's some randomization in the algorithm there. And we can also make sure that our degrees don't grow too much unnecessarily, in particular log squared n in the degree expansion as well. And that's a pretty good result. That's polylogarithmic in the metrics that we care about. So what's the problem? Well, the problem is that the topology of this complete binary tree is pretty fragile. For instance, if it is a tree after all. If node 5 were to crash, we can see that node 0 and node 8 are now disconnected in the real network. What does that look like in the virtual network? We've separated one entire node. We've partitioned the network, and that's going to be bad. So what can we do about it? Well, we can look at more robust overlay networks, say Chord. We're going to do that until we reach a legal configuration. So in Chord, a legal configuration is every node will keep track of a certain number of fingers, where each finger is a link to a node of exponentially increasing distances away. So we might have a link to a node that's 1 away, and then 2, 4, 8, 16, 32, etc., until eventually we go halfway across the network. So if we look at this node here, it's got a pointer to that one node that's 1 away, 2 away, 4 away, 8 away, etc. So we can build one of those networks and then allow us to be a little bit more robust. So we're going to define, more specifically, here's how we're going to build our Chord network. Basically, there's the fingers are just defined as the node's ID I plus 2 to the k, for k from 0 to log n minus 1 exclusive. We'll call that link, that j, we'll call that the kth finger of I. So again, it goes back, it's the diagram that we had shown in the previous picture. If we look at that, we can see that we can actually build the fingers inductively. So if every node has their 0th finger, then I can use the 0th finger of my 0th finger to build the first finger. And if everybody has their first finger, I can use the first finger of my first finger to build my second, and so on and so forth. So it turns out that I can actually build it pretty systematically and pretty carefully, provided I have a convenient mechanism to set up that first finger and then coordinate, connect the first of my first, the second of my second, etc. One way I could do that would actually be to use the avatar CBT network that we defined earlier as a scaffold to go ahead and build Chord in a predictable and a metered fashion. The metered part is important. We don't want to add edges too fast because it might cause the degree to go up too high. So what we'll do is actually just use a simple PIF type algorithm. We'll start in this CBT network. We'll send a command out saying, hey, build the ith finger. will then, on the feedback wave, nodes will go ahead and connect their ith minus first fingers together to form their ith finger, to form the next one in the list. So a pretty straightforward idea. We'll do that log n times and we have chord. There's two things, however, that we need to be careful about. Number one, can all nodes correctly determine the phase that they should be in? That is, if our stance is first we'll build CBT and then we'll build chord, can we actually ensure that? Can we guarantee that nodes will know what they should be doing? And then number two, if there's some time there where a node may not be building chord or may not be in the correct phase, can we limit the amount of extra work that it does? It turns out for both of these, the answer is yes. So for the phase determination, of course, nodes may begin and actually think they're in the wrong phase in a self-stabilizing algorithm. So we need to make sure that nodes can look around and determine what phase they should be in. It turns out that with that avatar embedding, if you're in a correct CBT network, a correct chord network, and any of those intermediate configurations from a legal CBT network to a legal chord network, all of those are locally checkable. And what that means is then in every faulty configuration, there's a node, and by faulty configuration I mean it's not a legal CBT network. It's not a legal CBT network that's starting to build chord, and it's not chord. If it's not one of those, then there is going to be a node within log n that detects that. And that means that once I detect that, that spreads, and so every node knows the correct phase within order log n rounds. Similarly, how about the degree growth? Well, the degree expansion for when we build CBT, we know that to be log squared of n, and every edge that we add, if we're going from CBT to chord, is an edge that's going to be present in the final configuration. And so that actually doesn't change the degree expansion. We don't need to factor that part in. So the only thing we have to look at is what happens when nodes think they are building the chord network from a legal CBT, but they're not, but that it is not actually a legal CBT network. It turns out that when we add edges using the propagation of information with feedback approach, at most we will add one edge per log n rounds, which, as we said before, is quick enough for us to only add a constant number of edges per node. So we at most double our degree before we realize that we're in an incorrect scaffolded configuration and can adjust for it. So yeah, putting that together, that means that when we use CBT as our scaffold, we actually have an algorithm, a self-stabilizing algorithm with a convergence time that's log squared n an expectation, and a degree expansion of log squared n an expectation, which is actually great results, polylogarithmic, the fastest out there for building the chord overlay network, simply by using this scaffold idea. In our full paper, we have a discussion about some of the things that are required for using other networks as scaffolds. Basically, we're looking for things where there's an efficient self-stabilizing algorithm for it. Nodes have low degree and low diameter, so they balance those. There's predictable routing that I can use to add the new edges slowly. And of course, the local checkability is huge. I need to have the ability to determine quickly if I'm building, if the scaffold is built, and if the scaffold is built, then where at in the building the target network, where at in building chord am I at? And we described, summarized those kind of in our paper. So yeah, in this paper, we went ahead and discussed how we could use that simple topology, that complete binary tree, as a scaffold for building more robust topologies, such as, in this case, the chord overlay network. We came up with a technique that is polylogarithmic in both time and space complexity, the first of its kind. And then we also, gave some criteria that people can use to help guide future work, either future work building more target topologies when starting from CBT, or future work designing more networks like CBT that would be good scaffolds that keep that degree low, efficient stabilization, local checkability. So I'd like to thank everybody for listening in to the talk. I'd also like to thank the reviewers for their very helpful feedback for the paper that just made it better. It's much appreciated. Feel free, if you have any questions on my talk, you're free, or on the paper, you can send me an email, andrew.berns@uni.edu, and I would be happy to talk with you. So I'll show the references, and thank you very much for your attention.